In the last video, we talked a little bit about what happens when you have current that changes with time and how that can influence a potential, a non-coulombic electric potential around another loop of wire. And we looked at that specifically for a pair of loops where the current is being turned on for the outer loop and it rises linearly. And what we found was that the potential that we develop around there, the induced potential, is a constant as a function of time. Now, the example we're going to go into now is a bit different because it actually uses what we call alternating current. And that is important because what we have worked with essentially so far is what we would call direct current or DC current. And this is the idea that you have sort of a steady, constant current. And it's really the kind of current that you would associate with circuits that have, batteries, but no real sophisticated stuff in them, no capacitors or inductors, but just resistors and batteries. This current, alternating current, is current that, alternates between two values, essentially. It's called AC. And it alternates between some maximum and some minimum, and there can be a variety of what are called waveforms, shapes of those things. But what we're going to focus on is sinusoidally varying current. We'll talk a little bit about that in a minute. There's an important historical sort of aspect to these two, which is that when electricity was being considered to be sent to homes, there was a discussion, a sort of very public discussion between Thomas Edison and Nikola Tesla about which of these kinds of currents was the most appropriate to send to somebody's home or a business. The idea was that there's a lot of money involved with being the sort of owner of the patent here and what would be used. But it turns out that alternating current is much better for long distance travel of electrical signals because the thermal losses, the losses associated with resistance in the wire, is about 1,000 times or so less than it is with direct current. And so you can send alternating current over very long distances as compared to direct current. So Nikola Tesla sort of won the argument there. Right, so the kind of current that we're going to be interested in is one that alternates between two points. And so maybe it has some sinusoidal shape like this as a function of time. And so here's a graph of the current as a function of time. And it has maybe some maximum I naught and some minimum minus I naught. And this would be one cycle of that signal, one cycle of that current. Now, the amount of time that we have for one cycle is called the period, and it's usually labeled with a capital T. And the frequency associated with this, how often this happens every second, is related to the period. So 1 over the frequency is the period, or 1 over the period is the frequency. Now, typically, we would model this sort of sinusoidally shaped current with a sinusoidal function that is something that has an amplitude of I0 and is multiplied by a sine function which varies between 1 and minus 1. So you can see where this would vary between I0 and minus I0. And it does so with a frequency of f. Now, this frequency f is related to 1 over the period, and therefore it has units of 1 over seconds, which are units of hertz. This is the thing that we can actually dial on a signal generator. The 2 pi is in here to help us understand exactly how the sine function works. The 2 pi times the frequency is what's called an angular frequency, and it is associated with how many sort of cycles, how many sort of circles you make per second. It's not what we actually dial on a function generator. This guy is. So we'll focus on this real frequency, which is in hertz, and the period, which is a time. Okay. So let's go back to the example that we were talking about earlier where we had 2 loops of wire, one big and one small. And what we're going to do is we're going to let that big loop of wire take on this sinusoidal current. So we'll have a big loop of wire that has some radius LG, RLG, it's the big radius. And centered on that loop of wire is another loop which has a radius RSM. Okay? And it's the exact same setup that we had before. The small loop is right at the center of the big loop. It's very tiny compared to the big loop, and it's in the plane. And so earlier we derived a result which described exactly how this situation works for an induced potential in this smaller loop. So what we'll do is we'll let this current run through the larger loop, and we're going to look at what the induced current is in this smaller loop as a result. All right? So that equation that we developed was that the induced potential difference around this smaller loop, given all the assumptions that we have, it being small, it being centered, it being flush, and so forth, is going to be related to the change in the magnetic flux. And again, we derived this all in detail in the previous video, which is mu naught pi r small squared over 2 r large. And then the only thing that varied with time was the current, di dt. So in the case that we had before, where we turned this thing on and we had a linear rise in the current, this time derivative was a constant, and so the induced potential around that loop was a constant, and therefore the induced current around that would be also constant in time. But with a current that varies sinusoidally, we will have to take a derivative of that. And you might have seen derivatives of sinusoidal functions in calculus. You can also just look them up. But the idea is that that derivative is going to be 2 pi f times I naught times the cosine of 2 pi ft. Okay? And so this induced potential is related to an induced current, as we talked about with Faraday's law before. And so we can rewrite the induced current in terms of the applied current, okay? And so what we assume first is that this ring has a resistance of R, capital R. That is, it has some resistance associated with it. And then we're able to sort of turn this guy around. So what we'll find is that that induced current, as a function of time, is going to be related to mu naught pi r small squared over 2r large times di dt divided by 1 over the resistance, and then there's that minus sign hanging out, which goes out front. Okay? Now, we can clean all of this up, and we can get an expression for that induced current. And don't worry too much about keeping track of all this, because we don't really care too much about the result, besides the fact that it's going to depend on a new sinusoidal function, and we want to compare those two things. So that induced current is going to then be equal to minus mu naught pi r small squared over 2r large. And then there'll be a 1 over r from the resistance, and then this time derivative that we have here, which has all this other stuff, right? So there's a 2 pi f I naught, and then there's a cosine 2 pi f times t. Okay? So at the end of the day, that's what we have. Now, how do we make sense of that? Like, does this thing actually make sense to us? Well, the first thing to notice is that a bunch of the stuff that's sitting out front of the cosine are actually constants. In fact, all of this stuff are constants. So the relationship that's really quite interesting is that the current that we drive the circuit with, that is the current that we're driving around the larger loop, is proportional to sine of 2 pi f times t, whereas the induced one is proportional to minus cosine 2 pi f t. So why is that interesting? Let's graph those two things, because this is actually really the heart of what Faraday's law. It tells us a lot about what's going on in that induced, that loop that has an induced current. So here we have a graph of the current as a function of time. Now, these two have different coefficients out front, so their scales are going to be different, but the time period is going to be the same for both of them. So the driven one is going to look like this, like a regular sine wave, whereas the one that is the induced one will actually look like a cosine. So it's going to have, it's going to start out big, it'll cross, It'll peak, and it'll cross again. And so it'll be shifted by a little bit, which is really cool because what we're seeing here is actually Faraday's law, the Faraday's law effect in action. As the driven current begins to increase, it does so less quickly. The rate of increase is smaller. So the induced current starts off really big because there's a big rate of change. And as that rate of change levels off, the current that is induced gets smaller and it goes through zero. Then the current that is being driven flips over. It starts to get smaller, but it does so increasingly so, right? It gets steeper. And so the induced current starts to pick up again. It's positive now because it's running in the opposite direction to the change in the flux. And it increases and increases and increases, and it maximizes sort of right here when this guy flips over again. And we see that happening for every cycle. So the idea is that these two match each other in the way that we would expect. That is that the induced current is, small when the rate of change of the driven current is small, and it's big when the rate of change is big, and it's exactly opposite the slope because it's running in the direction that is needed to reduce or increase the flux depending on what's going on with the driven current. So what we did here is talk about a specific example of a sinusoidally varying current around a loop and see what the effect was on a smaller loop inside that has some resistance. And really, we went through a lot of mathematics to get to this result, but the upshot is really these two guys and the conceptual understanding we're trying to get from what happens when we have this sinusoidally varying current that is driving it, and what is the response from the small ring. And how do those fit with Faraday's law?